One of the things I like to start my story out with is the puck will drop. The guys laughed whenever I presented this the first time. One of the things we come across all the time is the deadlines. They want us to get this building, has to be online, this date. My first dive into this was with Agula Ice Arena. It's our hockey arena that they built, it was 2013. I came into a meeting, sat down, and we were talking about all the things that are wrong with the building, what's happening with it, and it's about 2 weeks out from the first game, and the guy's answer to everything was the puck will drop. No matter what, that building is going to be full of people this date. Get whatever you have to do, get it done. And they got a lot of it done, but there were a lot of issues that took almost a year after to really analyze and dig into. And it took a lot of analytic collection of the data, the traffic, and everything to figure out what was going on in that building and why it wasn't functioning. As you can see by the numbers, we're a large infrastructure. We have 24 campuses, over 41 million square feet that we manage, which equates to almost 600 plus buildings that we're managing across those 24 campuses. We have a lot of student intake, a lot of staff that work across the campus, and this last capital plan was $3.28 billion. It was a large investment for the university, and that just finished up this year. We've gotten approval to do the projects for the next one, but they haven't given us any money to do it yet, so we're waiting to see if the money will come. This is what our summers look like. This is the time when students aren't around, there's nobody there, so they spend a lot of time constructing. And you can see everything yellow and orange in there is something that's being worked on during that time frame. So from June till usually end of August, all that work's being done. Roads are closed, you can't get across campus without having to take 3 or 4 detours. Our environment is very distributed, so each building is basically the way we're going with everything is isolating to a separate infrastructure. We want each building to be able to contain itself and run in distributed control. So that way if there's a network issue, we can still keep providing cooling, heating, elevators, whatever other pieces of the building that we're managing. With the deployment, you have everything else going on. So they want us to do a lot of things around analytics, collect this data from this, collect this data from that. But at the same time, we're still trying to do our day jobs of just maintaining the buildings, keeping systems up and running. All the construction projects happening at the same time. Contractors come in and do work on your campus, and they're just going to start tearing everything apart and don't really care about what else they're connected to. So in our large infrastructure, we see a lot of issues from one building affecting another. So we looked at different solutions to try to help us kind of take all these different tasks and try to consolidate them into an easy platform that's easy to deploy with the small crew that I have, and be able to connect it securely and bring that data back so we're not worried about people connecting in and causing us issues. One of the issues in the analytics that we just started on was alarms this year. February, I ran a report and started collecting data in a free open source product called Graylog. I was able to take the alarm data from the buildings, upload it into a central system, and start running analytics on it. And I was able to find out that 80% of our alarms are HVAC general, which are your basic, I'm out of temp, or I'm too low on temp. That's 80% of our alarms. So it's a lot of noise that we have 2 operators that are sitting there analyzing the system and trying to watch this coming in. And within all that noise, they got to pick out the criticals, which you can see PMI critical, and there should be HVAC critical. It's just a small little portion of that. So it ends up all that noise causes too much confusion. They're not targeting what we need to be targeting to get corrected. We have several facilities across campus. We have a bi-level 3 research facility. That is a very critical building. We're collecting vibration monitoring and everything on the equipment to make sure that the equipment's maintained. Anything that's done in that building has to be collected over the project and then also up to 2 to 3 years after that project's done, so that we can prove that that student wasn't exposed to something because of the negative pressure or positive pressure that happened within the space. We have precision equipment on campus. There's a laser in the bottom of the basement of one of the buildings that is a laser used for part of an atomic clock system that one of our professors has built. He is very critical about the specific temperature, everything. We're not allowed to take that thing down unless it actually fails. He wants it to go to fail. He won't let us do maintenance or anything on that system. So we're trying to collect the analytics side of it to try to show him that if you let us do the maintenance or give us maintenance windows to do it, we will less likely fail you and then have to take it down for days at a time versus maybe an hour or two. And then we have rare specimens. We have freezers that have ice cores from the last, I think it was almost a decade that they've been collecting glacier cores. These cores some of those glaciers don't even exist today. And they have these samples in freezers that we're currently monitoring the temperature in those to make sure that there is no issues with that freezer and that we respond in with a fast enough time to make sure that they don't melt. So what we're here to talk about, the predictive maintenance. And one of the reasons they brought me in for this is you have to have that backbone. You have to build that infrastructure to make the data get back to where you want it to. How to integrate it with other systems, with other departments. We work at the university. I'm an IT person / OT person. We're on the building automation side. There's a whole separate telecommunications IT group. There's a separate IT group for the Office of Physical Plant. There's a separate IT group for the core ITS stuff. So I have to interact with all those different people to get our data into other systems. We have research grants that are built off of collecting analytic data on a building and be able to show the full carbon footprint of the building. And that includes ceiling tiles, carpet, chairs, everything. They have to take all the data from all the different systems and everything, the way that building's built, and produce what is the actual carbon footprint of that building. And then run statistics on what they can do to improve it and how they can improve it. So it's that backbone to it that I'm here to talk about today. We had a flat layer 2 network spread out all across the campus. We had huge broadcast storms happening, causing data to be lost, traffic dropping off, and we needed a way to segment that. So we looked at several different solutions. We looked at NAC and your software-defined networking, firewalls, VPNs, all these different solutions. The problem is when it comes to scale. When you got to scale this across 700 buildings connecting back to a central plan, it's pretty difficult. And you see a lot of, that's where most products tend to fall flat, is when they go to that scale. We've seen systems, the connectivity start dropping off because we had too many VPN tunnels coming in. The firewall management was just, they had a central plane to manage all those firewalls, but you still had to go to each individual device and manage it. And it just became a very big headache, especially with this small crew. I have me plus 3 sysadmins and 4 technicians. That is it for my crew, and we support over 1,200 switches across those 24 campuses right now. And normally you should have at least double that, or if not triple that, to actually manage that kind of infrastructure. We're doing it with this small little crew. So the first part was secure, segment the network. So we use the tempered solution. It gives us it uses HIP protocol to basically lock everything down right after layer 3. So I can ping that device, know that it's online, but I can't tell what that device is behind it. And unless I have a crypto ID that matches it, I can't even do anything further than that. So that's what we did at our building level. Originally, the way Temper was designed is they actually put it in front of each of the control panels. The problem in the building is the way building automation protocol works, BACnet, it needs to communicate constantly to each other within that building. And it became a scalability again issue. You can't, trying to create the rule sets of who can talk to each other in the building, everything became a little too much. So we broke it down at the building level. So we have an entry level switch that everything aggregates through, and then from there to the data center is secured via the HIP switch technology. Correlate and analyze. So we wanted to centralize all these servers. We've had servers in buildings that were standalone. We had servers that were hosted in the ITS side, servers that were hosted at the core. Trying to tie them all together was a big issue for us. And so we built our own data center infrastructure, secured everything in with the HIP switch, and we're able to virtualize. We're at 90, I think we're at like 99% virtualized. I think we only have one physical server left that we are running, and which gave us the full redundancy. We have DR capability to be able to fail between 2 different buildings, full infrastructure, and right now we're replicating 18 gigs of data every 15 minutes, and it takes less than 30 seconds because we have 160 gig backplane between us, our 2 data center infrastructures. Optimize alerts, workflows based on priority. So this is where we started getting into the analytics side of it. We were looking at all these different things. The first step was we were looking at how we can start analyzing this data and get rid of the noise. So the first thing we did was with the alarms. We started taking those alarms and trimming them out. We started connecting elevators in. We take the elevator trip alarm and have it send a message to the work order system, which we run Maximo. It actually dumps it right into Maximo and issues a work order right away. One of the issues we had was overnight, there were kids getting stuck in elevators, not knowing that after a power bump, all you have to do is press a button and the elevator will move back up unless the power wasn't restored to that particular elevator. So we were having kids getting trapped in elevators not knowing that they just press the button and get out. So we wanted to make sure we're checking those. Whenever we do see an elevator go offline, power bump or failure or whatever, we want somebody to go out there. One of the funny ones is we found an elevator full of 26 guys. And it was all a bet, and so how many we can fit inside this elevator. Well, that tripped the 2,500 weight load on the elevator and forced it into lockdown, which you can't press the buttons, can't open the doors or anything. Took about a half hour for the guys to respond to it, but that work order was issued automatically to notify somebody that something was wrong. There shouldn't be that much weight in an elevator. We need to go look at it. So it's just amazing what you can start doing with this data once you're able to get it through on a secure infrastructure back to a central point and then just start running your analytics. Even if it's local analytics, can be helpful. And if you're running it through an open source product or somebody's, we looked at OSI Soft Pi and eDNA and all these different historian products, and they're so expensive, and do you need all that? And even some of them, they're just now reaching into that analytics world. So they were a database program or historian, and they're throwing analytics now on top of it. Or they bought somebody that was doing analytics, and we haven't really found the right fit yet. One of the solutions we're working with right now is we have all these different systems across the campus. Johnson, Honeywell, ALC, Siemens, we have them all over the history. And so how do we take all that data and aggregate it and bring it into a centralized system? We're working with one of our vendors. We're gonna bring it into them, let them do the normalization, take the temperatures and the freeze stats and all these different variables and tag them so they're properly tagged in a way that the analytics and the machine learning can start really doing something with it. Because we have in one of the systems, this is across 80% of our campus is ALC. In that ALC system, we have roughly 15 different names for a freeze stat. A freeze stat is a sensor that's on the outside of the coil. When the air is getting too cold coming into it, you want to close the dampers so that you don't freeze the coils. It's named FRZ, freeze stat, and I mean, several different names. So when we take that into analytics, it's going to be garbage. You're just taking garbage and dumping it in there. So garbage in, garbage out. So we started bringing it through this new system. We're doing a POC with them right now. They're a startup company. We're trying to figure out if this is the direction we're going to go. But if it works, it'll bring it in there, automate it, tag it, and then send it to the analytics package where then the data is normalized and we can compare across systems, and it's agnostic to what type of system's in the building. It'll only be whether we got heat wheel in there or we got reheat or whatever components in it. Those are going to be the only differences. It's an air handler, but it has these other plus components, and it'll tag it properly through that system. So here's we went through some analyzing the different costs, and the numbers didn't fit. When we started scaling out, and honestly, and you can ask Matt about this, I beat him up over his numbers. When we first started the project, the scalability, when we looked at the project total, we were talking millions of dollars a year in infrastructure costs. And so we worked with Temper quite a bit and figured out what is the best way to scale this and price this that makes sense when you go to 600 plus buildings. In the end, we're going to have probably close to 700 to 800 total HIP switches deployed out there in the infrastructure. As you can see here, here's where we use that capability of being able to isolate. Each building is isolated. So whatever happens in the building stays in the building for the most part. We only send out the data that's needed for the analytics or for the HMIs to produce the results for the technicians. And one of the nice things is this creates a tunnel from here back to our data center. So it creates the tunnel back to the data center. All of our systems are sitting in there running, but we can tell it, this can only talk to this. The HVAC can only talk to the HVAC. Electrical, only talk to electrical. So even over the same secure pipe, we're able to create trust relationships between the different systems. Some of the systems, we're actually bringing the electric meters right into the ALC product, or we're bringing it into the plant system so that they can get feedback on how the loop's doing, how the system is performing. One of the nice things we've been able to find, though, is the scalability and the rapid deployment. Last year in August, we were going to be presenting a similar conference, and I put it to my guys, how many buildings do you think we can do in a week? And we ran the numbers and we're like, oh, I don't know how many we're going to get done. We got 30 buildings done in a week. We actually were able to deploy 30 of these HIP switches. It was that easy to deploy. It was plop it in, create the relationships, and the devices were up and talking, bringing our data back into the data center. And in here, I like this slide in particular because you can actually see the segments. So you can see the elevator can only talk to the elevator. The lighting can only talk to the lighting. The only time we share out, you can see the FAS employees in the center there. For troubleshooting purposes, we can actually create instant access to a particular system for troubleshooting purposes. And all of our FAS employees have that capability that we can enable them to talk to the building controller or the outside air or the EOMS system. We can instantly tag it and let the two systems talk. The other thing we gain from it is instant isolation. If there's a building that gets infected, or even if our data center gets infected, I can actually, within 2 clicks, completely shut down everything and isolate each of the individual buildings. So they are blocked off and not getting any of the virus or infection.